I usually want to start here and tell you something about the challenges that we will see when we go to space, and then, for instance, where we have electronics in space. But now I see that my biggest challenge is how I can make it until 6. So this won't be possible anymore. So I hope that you can be a bit patient, and because I cannot go through the slides in just a few minutes here, but okay, maybe you will see later on. So let's start here with this nice picture on the title page, because people who know me know that I really love birds. So we see wild geese here, but we also see two things here that we already saw in the previous talk. And this is the moon, and also here on the right side, this is the Mars. So this is the destination where we want to go in the future, and I think we heard a lot about this before. So the interesting thing is that we also heard before, bringing something to space is not easy, and I want to say why. Now, why is something not easy to bring into space? And therefore, let's do a bit of rocket science in the evening. So let's start. So when we have here a rocket, because this is usually the vehicle that we use when we want to go to space, then we can finally start with, okay, we have here a nozzle. Where's the laser? Here's the nozzle. We have the nozzle. And in this nozzle, we burn some fuel, and there's always a portion of mass that is accelerated here in the direction of this vector u that we have here. So what we have is an impulse. No? So we have an impulse in the direction here of this vector u. And so this is the same. I think you know this experiment. You stay on a skateboard, you push away some mass. What you have is an impulse in the other direction. So you're moving in the other direction. So you have here now a velocity in the direction of v. So both are equally. So therefore, we can have here the equation here, some integral in the evening. No? So we have here just the integration of this one. And this gives us one of the most famous equation for rockets, and this is here the ideal rocket equation. So when you have to learn something this evening, so you remember this, please. So this is something that we know. So we have ln, no? This is here now the ratio between the mass that we have when we reach a certain velocity, and this m0 here is the mass at the beginning of our launch that we have. So this v here is the velocity that we want to reach, and this u here is the exhaust velocity of our rocket. So really interesting talk. No? You already want to left the room, but this is actually really important. No? The importance that we see here is when we now have a real example, like for instance, we have here an ant velocity that we want to reach because we have to reach it in order to not fall down to Earth again. Then we can also have a look on the velocity that we have of our fuel that we burn, in this case, hydrogen, for example. And what we can now do is we can easily calculate the ratio between the mass that we have at launch and the mass that we can bring into space. Now, this is given here by this equation. And then we see when we have this simple example, it's in the area of 17%. In practice, the issue is a bit bigger because we have also the structure of the rocket, we have Earth's gravity, we have aerodynamics, all this stuff. So therefore, the actual payload fraction is, for Falcon 9, for instance, roughly 4%. So we cannot discuss about this. Now you can say, yeah, but Elon Musk is building rockets, they are big and they are cool. Yeah, but you cannot argue here with physics. Yeah, so therefore, 4% is something that is more or less right now state of the art. When you go to the moon, it's in the area of 2 or even 1%. So first issue or first challenge that we see when we're sending something to space, it needs to be small, it needs to be lightweight. Yeah? So we heard it before, we cannot build an entire hospital in space. So therefore, we need solutions, and we have to keep this in mind. So now we are in space, and the next issue that we have is, we have a lot of issues there, but I do not want to talk about all of them. One issue that we have is, for instance, the vacuum environment. We already heard that. Okay, not really healthy for humans, but also not for electronics. You have outgassing effects, and for instance, the heat. So when you have the heat dissipation of electronics, how to get rid of the heat? So if a fan is worthless here. So therefore, these are big challenges, but we are not talking about these challenges because the sensors that we are developing here in the term of Spacepatch are in a pressurized environment on space station. So therefore, this is not a big challenge for us. But we have a huge challenge ahead of us, and this was already mentioned, the radiation. The radiation is coming from our sun. So we have a continuous solar wind that we can see from our sun, so mostly protons and electrons. But so the radiation here is, let's say, more or less moderate. No? So we don't have huge issues with this. We can easily shield this. Let's say this is okay for us. A more bigger challenge is what we see here, these nice looking coronal ejections. So you also might heard about the solar flares. So with these ejections, so a lot of particles are just thrown out from the sun into the space. And these particles are highly accelerated, have a high energy up to several giga electron volts. And this might affect our electronics pretty hard. Now we see later on why they hit our electronics pretty hard, but this is something that we have to consider. There we are also sometimes talking about space weather because these events are not regularly and hard to predict. So this is something that is in future also really relevant, also for human beings. So when we have these effects here. So then there's always something happening. So in space, there's always a supernova here and a star explosion there, and there's some collision. So there's always something that also accelerates particles going into space, and therefore what we have is continuous flux here of radiation that hit our electronic and then can reach several giga electron volts that hit our devices here. Good. So radiation is something that we usually do not think about, and yeah, we can also ask why. And so this is more or less a slide that I like to show. And the students, they are not, well, often they are looking like this because they have no idea what this is. This is a dynamo. Most people maybe know here this dynamo. And yeah, what has this to do with our not thinking about the radiation effects? This is pretty simple because we are not living in a yellow submarine, we are living on a big dynamo. Our Earth is a big dynamo. We have a fluid iron core that is rotating, and this induces a huge magnetic field around the Earth, and that protects us from the cosmic ray that we have. So our planet is actually a pretty nice place to live, so don't destroy our planet, because this is a good feature that you do not see on Mars, that you do not see in, for instance, also on Moon. So we don't have such a magnetic field here around the planets or the Moon that we want to travel to. Good. Yeah, so we have a protection field, therefore this is not a big idea, but what we want to do is we want to leave our planet and also our protection shield, with planet. And therefore, yeah, there were probes at the beginning that were flying through also the different magnetic fields and through this magnetic field lines here. And they observed that we have a further issue. So when you fly here through this magnetic field, you see that there are areas that are with, much higher charge and much higher energy on the charge that you can see, and these are called the Van Allen belts. So things are getting worse because particles are trapped in the magnetic field, they are accelerated, and therefore the energy of radiation here in this area is even worse. Okay, so when you now consider, here's the ISS, so we are really close to the Earth, so just roughly 400 kilometers. So here we are traveling above the 40,000 kilometers, so into deep space. And this is actually what we have to talk about, because when we are leaving the planet, in any case, we have to think about radiation effects. But when we are going far, far away, so on the LEO missions here, like ISS, yeah, there's already radiation, but this is something that we can still handle. So this is something that's okay, especially when I talk about this electronics. As the humans, you're okay. But when you travel through these Van Allen belts, it gets worse. But this is just a temporary effect, so okay, we can also handle this. When we travel to Moon and Mars, well, then it starts, because we have not a protection shield, so we are more or less unprotected against this cosmic ray. And yeah, Markus Braun already told us before that this is something that affects our humans, but I'm also thinking about my electronics. And my electronics is also affected pretty hard. So next nice slide. So don't be worried about this slide. I try to go a bit deeper into the radiation effects. But on the next slide, you will see more or less a summary, which is pretty easy and the only thing that you have to remember. What happens? We have particles. These particles, they strike here our electronics, and our electronics is usually built up on CMOS technology. Then we have different effects that can happen. Several effects, I only want to tell you 3 today. And one effect is the total ionizing dose here. And this appears whenever we have, this is barely working here. Okay, this when we have here our particle that strikes our isolation, so our isolation layer here between our field effect transistors. What happens is if the energy of this particle is high enough, above the Fermi energy of the silicon dioxide, we are forming here in our silicon dioxide here electron and hole pairs. This electron and hole pairs is not a big issue because they recombine, especially when you have here at your gate. Oh my gosh. Okay, anyhow. When you have here on your gate a voltage level, so then the electrons will flow pretty fast to the gate, and the protons or the holes will just move slowly down here towards our surface layer. The issue is that the surface is not perfect, and so we have here particles that are trapped. So we have here an increase of our surface charge. Why is this important? This is important because here our surface charge that we have as an accumulated effect due to the radiation that is trapped here increases, and therefore our threshold voltage decreases. That we have here is then therefore decreased. And when we decrease here the threshold voltage by this radiation that is accumulated here, then we have a stuck error on our transistor. Forget about all the slides. This is what's happening, and this is the only thing that you have to know. The particle here is accumulated on our chip and therefore leads to a decrease here of our threshold voltage, and therefore in the end we have stuck error. So our transistor is damaged and we can not repair this. This is permanently damaged. Another effect, the single event upset. This is more interesting also for us in our research, because what happens is that now this particle strike went through the entire silicon again. So we are forming here electron hole pairs. And what we then see is that these electrons that are separated now will flow here in the direction of the drain. And if we have a directed flow of electrons, this is what we call a current. So therefore here in our transistors, what we see is an increased current. And this current can lead to a malfunction of the transistor itself, because what happens is that in the end, we see a bit flip. So it seems like the transistor is switching, although it is not. So therefore, remember this slide here. The things that will happen is if we have here the particle striking our chip, we will see bit flips. And this bit flips is a thing that is really important to know, because we have issues on our information. So therefore, we are maybe losing information. We have corrupted information. During storage, when we store data, we can lose also this data. So therefore, this is something that is interesting when it comes also to the signal processing part. So how we can protect our signal processing, although we have here faulty data or potential bit flips. Last but not least, a really destructive effect, the latch-up effect. So therefore, you have to go also again here in the CMOS layer. What we see is this happens for the technology where we have bulk CMOS. So we have here a high dope base material. And what we have is that here, we have transistors that are forming, bipolar transistors, just to this your technology node that we are using. So we have here an N-dope material, P-dope material, an N-dope material, and this is what you know from other lectures. This is an NPN field effect and not field effect bipolar transistor. So when we put everything together, what forms out of this is this so-called thyristor. And what happens with this thyristor is we have now here a particle strike inducing a current. We already know how a current is induced by particles. Firing this transistor leads to the effect that we will have here also a base current on this transistor. This transistor is also fired, and so we have a self-holding loop here. What it means is that in the end, we will have here a short between our VCC and our ground. And that means, just remember this slide here, the particle hits our chip, and this could also lead to the effect that an entire device might burn. So they are not burning, but thermally damaged, let's say it like this. So this is a worst case scenario, and then also the device is corrupted. But really depressing. Everything is going really challenging in our space environment. But let's get back to our dream that we want to have. And we already saw before that this is also a vision. So, maybe this is a bit too futuristic, but we also saw that there are upcoming missions that are, I guess in the next upcoming decade, we will see for sure. And I know Artemis is pretty close, but we also see here Artemis. And I don't have to talk about all the challenges for the human being. So when we go for astronauts, then it is also really, really important that we have technologies that support
the healthcare, and we already heard in the previous talk that this could be done by, for instance, sensor technology. And now we remember our challenges. So we need lightweight solutions. So that's why we focus on wearables. And we need also reliable operation despite the fact that we have here radiation that not only affect the humans, but also pretty hard affect here our electronics that we have. Good. So this is Spacepatch. This is what we are doing in our this is the research object. Pretty nice small variable that we designed, but there went a lot of research into, especially for the selection also here of the parts. So these are still COTS parts, so it's not possible to build radiation hard variables here due to several reasons that I don't want to explain too much in detail here. So therefore, we have here a carefully selection of COTS parts that we used here. We have here a cardiac sensor, so based on the 6 DOF sensor. I tell you a bit later on a bit more about this one here. And here we want to achieve cardiac monitoring. So we split up the processing part. We have an FPGA here on board. This is this tiny device here, a small FPGA here, and we have a BLE SoC. So also for software processing, we can do something. And if you want, you can also send the data wirelessly to a crew laptop or to a crew tablet or something like this. Really important is also that you can safely store the data. So when you cannot send them away, they have to store the data here. So therefore, it's also an onboard memory. But again, always we have to think about that we might have bit flips and stuff like this. So therefore, here we have a lot of protecting codes, for instance, a forward or a correction by using Reed Solomon and stuff like this. Yeah, this is also already based on flight heritage. So we had partially things on ISS already. And then from next week on, we also have an IOV of this entire device here on the Morpheus rocket that we also somehow saw before. Good. I cannot go into all the different aspects that we are doing research in this device. This is too much. And then I think Professor Smirnova will also carry me out here somehow. So therefore, I will just briefly go into some things that we are doing here in our group. And one thing that we are focusing on is how can we detect radiation errors that are happening in our FPGA structure. So FPGAs are pretty nice in space. You can implement your own hardware. You can implement your own mechanisms in order to be protected against SEUs. But it could also happen that you have your issues and you want to detect them. The next issue is that on this scale, this FPGAs that we are talking about, the possibility to make debugging on this device is limited. So therefore, we have to find a method which we can use in order to read out here errors that might occur here in our fabric. So what we have implemented here is a really simplistic test core. So the test core is located here in the FPGA, and the test core can wrap around some IP cores. So the IP core are actually implementing the functionality. So for instance, later on, the SPI cores that we are using for the sensor, or we are doing differential sensing. So some calculation blocks can be also wrapped around here. And then we can use here the test core in order to perform some kind of in-system testing. So this is not the newest idea, but what we are doing here is we are separating the direct in-system test by having here the connection to our external controller, which is here our SoC that we also have here. So connection that we have here between the controller and also the core is protected with error-correcting code. So we are using repetition codes here. So therefore, usually between the communication of the test core and the test controller, this is external controller, there should be nothing that should affect here our testing. So this is the test core from the inside. So again, you don't have to understand everything here. It's just to impress what we all implemented. The interesting part that is written down here, that this entire test core uses just 77 lookup tables. So it's really tiny and really lightweight. And this is what we want to achieve. And it's flexible. Then we can wrap it around some IP cores that we have here on our implementation. And so it's also future proven that when we have other IP cores, we can just adapt here our test core that we want. It's dual redundant, so when there is a bit flip or some other radiation effect that we see here on our fabric, the test core itself is not affected, or at least we can recognize that there was an error. This is also really important. Yeah, and as I said before, the communication is also protected. The biggest issue that we had during testing was that how to test. Because radiation test is really expensive. So therefore we thought, okay, how can we do this? Yeah, fault injection is not possible. We have no debug interface. And so we came up with the idea that we say we're using undervolting. Yeah, so we just reduce the voltage level, go much below the specified voltage level, and then we provoke errors on the device. And we actually see that here our test core can detect these errors. We also did some radiation tests. This was just an electron beam, so we can only go for this TID testing where we are hoping to see some effects. But actually the FPGA that we selected, so we had to stop at 70 kilorad because we cannot see any error on this device. And then the beam time was over. It was almost, I don't know, 1 o'clock in the morning or something. So we had to stop here this test. But there is an upcoming test in, let's say, January, February next year, where we also want to test the SEUs, and then we see the effectiveness of the test core. So just briefly, really briefly, what we are measuring, because right now it's just electronics. So what we want to measure is SCG, so seismocardiography. The idea is not new. So we have our heart, which is pumping, and then it is evoking a ballistic force that is propagated through your body, and on the surface of your body, you can measure it by using, for instance, simple accelerometers. So here you see an ECG, so this is probably what you already know from your doctor, and the BCG, which gives you the actual movement, at least on the surface of your body, of the heart contraction. But the issue is, again, that we have also here some challenges. The acceleration that we can measure is really low. So it's close to the noise floor of this usual MEMS sensor, so therefore we have to think about methods how we can improve this. The outcome would be really interesting because this gives you a much bigger insight into the cardiac functions like valve openings and closing and stuff, but I'm not a physician, so therefore this is what I've been told. But therefore we have to have sensors that can actually detect these things. And in future for us, which is really a nice challenge and really something that we love to do, is the signal processing directly on the sensor. So it's a huge playground for us. But we are still right here. So for the first challenge, this is something that I will not go too much into detail because this was something that I already discussed here in a bigger scope. What we do is we are using not just one sensor, we are using two sensors. And what we do is we are putting them in a differential orientation. The first thing that we can do is we can think about the oversampling theorem. And the oversampling theorem says that we can here now have an SNR improvement of 3 dB. So we are lowering the noise floor by just using two sensors. The other thing, think about the space environment. We have an inherent fault tolerance. So we have two sensors. We can detect errors. And the other thing that we can do is that if we have here a fault injection by, for instance, a particle hit that we have, this will also lead to a common mode interference. And this is what you also can see in the spectrum of the acceleration. And therefore, when we have a differential orientation, we can now reduce also here these glitches that we have due to some particle strike that we see. So therefore, you see here that we can also rule this out. The good thing is that therefore we did an FPGA. We have it on board. So this is implemented. This is working probably fine and has already here some flight heritage also on ISS. So long story short, I hope in this few minutes I was able to show you that it is not that easy to implement electronics for a space environment. So this is something that also, let's say, the manufacturers of satellites and also for the bigger classical space electronics are totally aware of. So this is nothing new. But one thing that I think is overseen is all the little gadgets that astronauts have to wear in their daily life, like a Fitbit or maybe some other device that monitor your daily behavior. This is still all commercial. And this is also okay when you go on ISS. But this is not okay when you go for deep space missions. And this is something where we want to close the gap, where we want to implement some variable that is actually space capable, also for deep space missions. And therefore, there are a lot of ongoing work. So this is not everything. So there's a lot of things in methods for reliability and also for fault tolerance that we're implementing, especially for storing the data. This is a big issue here. And then for sure, there's a lot of things going on here in the signal processing domain so that we want to increase the efficiency by not just recording data, but also to implement the feature detection directly on the sensor itself. Another thing that is also going on. So We will do some measurements next year for the formation of SEG signals. So SEG itself is also really interesting research topic, and therefore we will perform also some zero-G flight next year in order to see what we can gain here in terms also of an algorithm that can correct artifacts that are formed here in gravity environment. Yeah, going back to space, so we are right now doing the qualification process so that we can actually send also these sensors into space. And as said before, the Morpheus launch will be then next week. Yeah, and then we already heard that there is some discussion about the Artemis mission, but this is something which is out of my hands because I'm just a scientist and therefore not a politician. And yeah, I hope that I can show you that everything is not quite so simple, but we all know that it's technically possible.